Good afternoon. Welcome to New Vulnerabilities in 5G Networks here in South Pacific with your speaker, Altaf Shaik. Before we begin, a few brief notes. Please stop by the Business Hall, located in Mandalay Bay, Oceanside, and Shoreline ballrooms on level 2 during the day, and for the welcome reception tonight at 5:30. The Black Hat Arsenal is in the Business Hall on level 2. Please join us for the Pony Awards in Lagoon JKL at 6:30 p.m. And don't forget the merchandise store on level 2 and session recordings from Source of Knowledge. They have a desk on every level of the conference. Please put all of your phones on vibrate, which makes it easier for us to ignore the ringing while you wait for your voicemail to pick it up. Now please give a warm welcome to Altaf Shaik.
Welcome back, everybody. I hope everybody had a great lunch, maybe heavy lunch. Okay, so I'm Altaf Shaik, and I'm actually a PhD student at the Technical University of Berlin, and my co-speaker Ravishankar, a research scientist at Sintef in Norway. Unfortunately, he was not able to attend Black Hat, like some family emergency, so I'll be doing the talk. So as the title says, we found some new vulnerabilities in 5G networks, so we'll be talking about that. We all know like the kind of hype 5G has today, I think even bigger than this room. So everybody is talking about 5G, what is it? And even my friends like who doesn't know anything about technology, who is working in banking sector, like keeps asking me like, what is 5G? Then what's happening in the news? Like I think you all know what's happening in the news regarding 5G and its deployment. So it's kind of crazy, but we found some new issues, and then I'll be talking about that. So the beginning, I just give a short overview of how 5G security looks like and the kind of threat landscape we have. Following that, I talk about the kind of are IMSI catches really possible in 5G and what can we expect in the future. And I finish with the kind of new vulnerabilities we found in 5G and how we got them fixed and all this stuff. So basically, 5G is for machine communication. I mean, not only machine communication, but because like we had 2G, 3G, and 4G, everything which was used for human communication, but 5G, I think it takes another level where it's actually being designed for machines to communicate. For example, we take autonomous vehicles or even low latency communication devices, like for example, IoT. So all this stuff, it's made for machines. So if we go a bit, okay, there is a lot of stuff about like 5G, it's so much bandwidth, it's high speed, all these things, but putting them aside, talking about security, 5G had like some strong security requirements. Obviously, it should be better than 4G. So same way, there are three elements in which I would like to present like in 5G security. The first one is we have new use cases, like so many use cases that are actually depending on 5G. Like autonomous vehicles, IoT, many different industries, many use cases, ultra reliable low latency communication, mission critical communication. So there's a lot which depends on 5G. To actually facilitate to have all these use cases successful, we need different kind of technologies on the core network. For example, like we have different technologies like software defined networking, then NFV, the network, like the virtualization technologies, then network slicing features. So these are some new features which are coming into the core networks, which never existed in mobile area or like mobile network area, and they are somehow coming into reality with 5G. Plus, we have the LTE security requirements. Comparatively, compared to 2G or 3G, LTE was much more secure, although we saw so many attacks on LTE, but encryption and integrity protection wise, like authentication wise, it was much stronger than what we saw in 2G and 3G. So all these requirements build up the whole 5G requirement set, and we have to see in the upcoming years, like is 5G, would 5G be successful in actually making these requirements a reality, or can the attacks in the past like repeat? Like for example, like IMSI catcher attacks or location tracking attacks. I think we have to wait and see for this. Okay, so there are different elements in 5G security. So I just brought it like three different ones. The first one is the cell level, where we have so many different devices, not only phones. We have cars, then we have smart homes, then we have different IoT devices. Then We have different type of base stations. Like previously, it used to be a bit centralized. Now we have a mix of centralized base stations and then distributed base stations. So there is a whole lot of like different devices will be scattered, like millions of devices will be scattered around us. And this will be managed by a kind of, kind of having the edge cloud, which actually facilitates the speed of having different applications. Like you'll see in the future, like how it's possible with different applications. Then we have the central cloud, which we call core network, but this will be completely changed into something like cloud-based, where you have all this virtualization technologies, network slicing, or for example, let's take a simple case where an IoT provider, like service provider, would receive an access to actually install his own applications directly on the network operator's hardware. So basically, this is something we call like network slicing. Each kind of application is receiving a slice, and the security of the slice or the operations, the kind of speed, all this could be configured in real time, and this is something the operators and then the service provider like have to discuss. So this is something we call it like network as a service. So today I'll be talking more on the radio part, the over-the-air network level part. So if you look in 5G, there is a lot of changes, like there is improvement in integrity protection, there is improvement in privacy, like for example, hiding the permanent subscriber identity, which is IMSI. Then we have improvement in resilience, like for example, if what happens like when certain messages like which are not protected are kind of misused, like how do you deal with such kind of scenarios are somehow addressed in 5G. So there was a lot of improvements, and we will look into that mainly in this. I would be talking in this region. So if we go back, just see how security has evolved from 2G to 5G. So the first one, 2G, the straight statement, like there's no mutual authentication, so false base station attacks are simply straightforward. And even today, like there are so many commercial IMSI catcher, like Stingray type of devices that still use 2G to intercept voice traffic. And then we have 3G, which improved. There was a mutual authentication where the phone and the base station authenticate each other. This somehow can eliminate, okay, this doesn't really eliminate the problem of fake base stations. Still, you can operate fake base stations. Then we have the 4G. We have mutual authentication, the same which was taken from 3G. Then we have integrity protection for the control plane messages exchanged between phone and base station. Also, similar thing applied in 5G, but a little bit improved in the terms of mutual authentication, like trying to prevent fraud attacks, like location fraud attacks. The same kind of algorithms which were used in 4G were reused in 5G. They're also still working on 256-bit encryption algorithms, but this is something I think we have to wait for the future. So security has changed a lot when we are moving from 2G to 5G. So obviously we expect that 5G should be really stronger than 2G. So when you talk about like attacks in cellular networks, the common device or the common thing you call is like IMSI catcher. So this is something, in the beginning it used to be like a device which is harvested for collecting identities or SIM card identities or even IMEIs, or not only IMSIs but also IMEIs. So this reveal information about the subscriber and the device. And later, like they also use the term IMSI catcher for voice interception attacks or even location tracking or different kind of attacks. But this one was mostly on the air interface attacks. We have something else on the core network side, like SS7 attacks or even diameter-based attacks, but that's a different story. So if we look on 2G, like the IMSI and the IMEI was available in clear text for any kind of attacker. Like for example, even a passive attacker can actually obtain IMSI and IMEI. Then we moved to 3G, the same, like IMSI and IMEI was not given any protection. Maybe it was not a priority then. Then moving to 4G, like there was kind of protection which was available for IMEI. So any rogue attacker cannot actually access the IMEI of any phone or any kind of device. This was protected in 4G. Moving to 5G, both of them are hidden now. So they kind of encrypt IMSI and trying to call it like SUPI. It's like a concealed identifier. So the problem of IMSI catching, like just the word IMSI catching, is solved in 5G. But encrypting the IMSI is something that's optional, and it's up to the network operators like to implement, because this takes a lot of effort, because you need to have a kind of public key in the SIM card to actually encrypt the IMSI. So this will take time to actually see it in practice. So I'm actually still waiting for that, like to see somebody implement that, and then we can somehow give a test. So talking about like 5G security, yes, it is definitely better than 4G. And there were a lot of attacks or a lot of vulnerabilities which were fixed. For example, like the downgrade attacks, or some other denial of service attacks which were fixed in 5G. Then location tracking problems were fixed in 5G. But the 5G was using the same algorithms, but I would say like maybe a little bit enhanced. Like there could be new algorithms, but at the moment, like they are the same algorithms from 4G. They are reused, and there could be a stronger ones which might come up. But it's something that's not fixed in 4G, so obviously it's taken to 5G. So why I say this is because there are the similar kind of protocols which started from 2G, then they were taken to 3G and 4G. So the way or the protocol stack that behaves in mobile networks like never actually changed. But there were a lot of improvements in terms of like authentication, encryption, and integrity protection. But if you don't fix the main problem, like you still see the attacks happening again and again. So one kind of IMSI catcher attack in 5G we actually presented this in last year Black Hat. So this was tracking the location of, or tracking the presence of a particular SIM card in a particular location. So this was still possible on 5G, and there is still some discussion going on in the standards, like trying to address this problem. So I'm going to talk about something new which we figured out. So this is called capabilities. So when I'm telling like capabilities of a modem, I'm not talking about the processor we have in the phone, or the speed of the RAM, or nothing like this. I'm exactly talking about the capabilities of a modem, like what a modem is actually able to do. So we have like two different capabilities of the modem. Like these are actually defined in the standards. These capabilities are defined in the standards. And like I also mentioned the standards in the bottom, but okay, there are two different capabilities. The first one is the core network capabilities. Then the second one is the radio access capabilities. So the first one is the core network. So these capabilities include like the security algorithms that are supported by the modem. Then does the modem support voice calling features, or does the modem support SMS features, and does the modem support like V2X, which is coming maybe in a couple of years, the automotive vehicle features. So we are going to see this in 5G, or maybe 1 or 2 years from now. Then talking about the radio access capabilities, the word itself describes it. Like for example, what kind of frequency bands it supports, then the RX and TX features, then does it supports like multi-input, multi-output features. So these are some of the features that are really responsible for the high speeds we see in 4G. And also something called category. So if you take the word category, there are like 20 different categories in LTE. And if you increase the number of the category, for example, if you take iPhone 10, which is a Cat 16 device, or if you take Samsung Galaxy S4, it's a Cat 4 device. So as the model increases in its capacity or price, the category also increases. So these are the two different capabilities that exist in the modem. As a normal user, as a smartphone user, or we don't get to see them because they are inside the modem, inside the baseband processor. So a little bit more detail, maybe if you want to, you could actually access it when you're reading slides. So there are different core network capabilities. For example, like the voice calling capabilities, the SMS supports, or what kind of voice codecs it supports, like AMR, half rate AMR, or full rate AMR. Or for example, like when you take a USB stick, USB dongle, it doesn't support voice calling features. Like it only supports the data features, maybe SMS. So So some of the new capabilities like which are coming in 5G, for example, we call it like CIoT, cellular IoT. This is not really 5G, but this is like I think the final releases of LTE, like release 13 and release 14. Then we have V2X features, which will show up in a couple of years. So these are really like 5G specific. So these capabilities are existing in the modem. And then we have the radio access capabilities. Like I said, there is a category. For example, this modem capabilities are category 4. And there are different capabilities like physical layer parameters, RF parameters. So there are like thousands of parameters or like optional features defined for the modem. So basically these are designed by the baseband manufacturers, for example, like Qualcomm or Huawei, Intel, or so they actually read the standards and then define it inside their modem, like they program it. Okay, so basically these capabilities are actually sent to the network whenever your device is registering to the network. So let's start with the basic registration procedure. You turn it on, and then the first one is like the core network capabilities are sent to the network. Then the core network is doing authentication and security, very good. Then the core network is actually asking the device like send me the radio capabilities. Okay, it sends the radio capabilities. Then it performs the over the air security like encrypting and integrity protecting the communication which is happening between the phone and the base station. So the encryption actually starts after sending the capabilities. And then finally, if everything goes well, then registration success, and then you have data access and everything. So what we see here is like these capabilities are actually sent before setting up the security. So which means that an active attacker can actually obtain these capabilities, or a passive attacker listening between the phone and the base station can also receive access to these capabilities. So both passive and active attacks are possible in this case. So we tried to do some passive and active attacks in this one. So what's the issue was like, the issue was these capabilities are accessible by fake base stations. You can easily set it up on 4G or 5G. And then the second thing is like they are sent in plain text to the network. And then we found some standard and implementation problems like that allowed us to exploit these capabilities and then do some other attacks. So we did like 3 types of attacks. The first one was mobile network mapping. We call it like Nmap. So this Nmap is something similar to the Nmap that you see in traditional IP. I'm going to explain it like in the coming slides. So then the second type of attack we are doing is the bidding down attacks, bringing the user down from 4G to 2G or even from 5G to 2G. Then we have battery drain attacks, which is very, very dedicated to narrowband IoT networks. I'm sure like you must have heard of this narrowband IoT term quite often these days. So to do some attacks, like we try to set up the whole, we created like a test bed. So like I said, we did a man-in-the-middle attack because we are trying to modify the capability. So I'll explain you that. So we used 2 different USRPs with this. Then we used some open source software that was available from SRSLT guys. Like thanks for their great work. So we set up a whole man-in-the-middle relay. So basically we have the phone side, then we have the base station side, which is relaying all the traffic from a legitimate phone to the legitimate network. Then we tested this on some of the commercial networks, actually across Europe and US and some other countries. For testing, we use so many devices, I think roughly around 80 to 90 devices, like different types of phones, different types of modems, laptops, because they also have modems inside. So the first attack, like we are trying to do Nmap. What does an Nmap do? It gives you information about the live hosts which are connected to your network. The kind of information is like what kind of ports, what kind of operating system it's running, or what's actually happening with that devices in that network. So we try to do the same thing, like we try to run a fake base station or a passive attacker that's actually trying to receive the capabilities of all the devices in the surrounding and try to estimate or intelligently guess the kind of maker of the baseband, the model of the baseband, the operating system it's running, and the kind of applications it's running, and if possible also find out the version of the operating system that's there. Um, so basically, this is the kind of the tree we built. It could be user specific. For example, like I built the tree like this because it was convenient for me. Maybe somebody else might find out something else differently. So basically, we are trying to find out the chip maker, then the device model, operating system, application of the device, then the baseband software version, also the application operating system version. So first we find out the baseband model, then we find out if it's a cellular device or if it's a cellular IoT device. If it's a cellular device, is it a phone or is it some other device? If it's a phone, if it's an Android, iOS, then if it's Android, then what kind of Android is it? Samsung, HTC, LG, Nokia. Then if it's iOS, like if it's an iPhone or an iPad, or what is the operating system version there? So we also try to get that. Then if it's other kind of device, is it a car modem or if it's a railway modem, then is it a router, USB dongle, or is it a laptop, or is it a vending machine like a typical IoT device? Or so if it's not a cellular device, it could be a cellular IoT device because these are the only two categories exist. It could be either a narrowband IoT device and LTE-M device, but these are quite new in the market. I don't expect them to be in huge numbers compared to phones we have. So this is kind of the kind of like Nmap we are trying to do. Basically, you can ask me the question like, how is it possible? So there are two things. The first one, like I said, the baseband manufacturers implement these capabilities. So there are handful manufacturers, for example, like maybe 5. We actually considered 5 in our experiments, like Qualcomm, Huawei, Intel, Samsung, and MediaTek. We find they have the big market, so they implement the capabilities differently because the capabilities are optional to implement. Not all of them are mandatory. Some you can skip, some you can implement. It's up to the baseband manufacturer. Some can be enabled or some can be disabled. Then the second one is each target application requires a different set of capabilities mandatory. For example, you take a phone, it definitely needs the voice codec facilities. Or you take a USB stick, it definitely needs the data capabilities, like the data transmission reception capabilities. Or you take a car, like a latest car, it needs the V2X capabilities. So there are different capabilities that suits an application. So these are some of the like the fundamental things that allowed actually us to do some fingerprinting. So we like I said, we selected so many devices. We also had some devices, some military devices, which showed really different capabilities than the traditional or the commercial ones which we are using. We also had modems from cars. Also, like you see on the left, it's full of phones, different phones. Actually, the list is very huge, but I just put only some of them. Then we have different routers, different USB sticks, different laptops, so many devices, like maybe somewhere around up to 80. So we actually collected the capabilities of all these devices, create a huge reference model, and then when I'm actually saving these capabilities, I try to save based on what was the baseband manufacturer, because in this case I know I'm building the reference model, so I know everything about in this device. So once I have all these capabilities from so many devices, I started analyzing, like looking into that and trying to find fingerprints that allow me to actually differentiate between these devices. So the first fingerprint was to actually identify different baseband vendors, like to find who is the baseband maker. So if you take this table, so like we have different capabilities listed on the left. If you take the second capability, which is called EIA0, it's a null encryption algorithm. It's actually optional to have this. So if you take, in this case, Qualcomm was the only baseband manufacturer like to actually disable this in most of the devices. Maybe roughly like 99.9% devices we see it was disabled. The rest of the basebands, like it was always enabled. So this could be a good fingerprint to actually identify if this is a Qualcomm device. You take other, for example, like there's something called extended measurement capability. So this was used in 2G networks. This was only enabled in MediaTek. I don't know the reason why, but it's up to the baseband maker. Like, so if I have to find out the reason why you implement and why you don't implement, it takes, I think, so many ages. Like, because there are like hundreds and thousands of capabilities which are optional and then mandatory, or it's up to the baseband vendor to implement them. So this is some fingerprints to actually identify different basebands. And once you know the baseband maker, you can easily say, based on the capabilities in that, you can actually tell what kind of model is that. For example, like Snapdragon 830 or Snapdragon 820. Once you know that, you can actually, there's a nice wiki where you can actually see which devices are actually using this particular baseband model. So then you have a list of devices, maybe 10, 20, or it depends. So once you get that, now it's the time to identify the application of the device, like a little bit more higher level, like what is the application? Is it a phone or is it like a router or something? So there are some easy differences, like to identify between a cellular device and an IoT device. There are certain timers which are always active or mandatory, should be present in IoT devices. For example, like PSM timer, this is something mandatory for IoT, which is not mandatory for, because this is something to save power, which we don't need for phones and cars or something. Then we have different, because like we wanted to identify phones specifically because there are so many of them. So phones obviously have this voice codec feature active. Then when it's connecting to the network, it obviously enables the fact that it has voice domain preference. Others, like sometimes like it is present or it's not present. So then sometimes like you might be wondering, okay, normally like there are phones which used basebands only from a specific manufacturer. Like for example, if you take Huawei, it only uses baseband from Huawei. Or Samsung only from, I mean, Samsung can also use Qualcomm baseband, but it also uses a Samsung baseband. Then Apple, only two options, like either Intel or Qualcomm. Then there was, okay, this went a bit tough, like trying to find out the difference between Android and iOS. Like this is something really needed. So there are like two features which somehow looks like the MS assisted GPS. This was a feature in 2G, and then this was actually disabled in iOS, maybe privacy reasons or I don't know. But this was always enabled in most of the Android devices. So okay, this is the positive side of doing this fingerprinting. Like there could be also issues we faced. For example, like in cases when there's a SIM card, like the SIM card can actually control the enablement or disablement of these capabilities. Like for example, like you said, maybe SIM card can actually control what kind of bands can be active or what kind of codecs can be active. There are bits which you can actually enable in the SIM card which actually controls the baseband. So SIM card could be a little bit tricky part when you're doing this fingerprinting. So sometimes like there could be situations where the capabilities between different devices are equally matching. So there's nothing to worry. We have like thousands of capabilities to actually differentiate between them. I just showed a subset here. But if you refer to the white paper, like there are so many different capabilities that actually allow you to differentiate easily between so many devices. So what now? So if you're able to find out the operating system version or the kind of operating system it's running, the kind of device it is, you could plan a targeted attack. Or if you're looking for a specific device, like I said, some devices, for example, if you take devices which are used in field testing, they have completely different set of capabilities from the traditional devices which we see in the market. So if you're looking for some specific devices, it is easy to find with certain fingerprints. Or if you are looking for a military device, it is also easily, I'm not showing them here, but if you're interested, we can really talk about it. So the good thing is, like, we are actually trying to release this tool, just open it, but not the man in the middle doing thing part, but once you have the capabilities, how we create an automated tool like that actually analyzes and then gives you an Nmap like result, like in the end. You just feed the capabilities and then it will give you what kind of device it is and then what does it do and all this stuff. So this was the first fingerprinting attack. Then the second one was binning down attack. Like I said, the capabilities are actually the radio access capabilities, which actually define the speed that your device is receiving. For example, like you take an iPhone, which is an iPhone 10, like it's supposed to receive speeds, theoretically it's supposed to receive speeds up to 1 Gbps. theoretically. But some networks, like, they don't support that speeds yet. So practically you might see, maybe in busy hours, like you might see maximum 60 Mbps or 70. It depends on the network operator and the kind of, maybe if you're operating it on the midnight, like you see maybe 200 Mbps. Very rare, but if you're lucky. So the radio is something that's actually controlling the speed of the speed what your device is getting. So if you try to kill that radio thing, you are really affecting the service that's actually to this device. So in this case, like, the network is actually asking the base station to get the capabilities. So the phone would actually send the capabilities. So if we are operating a man-in-the-middle relay, so there's a relay in between which is trying to modify these capabilities, because in this case, the security is actually kicking in after the capabilities are sent to the network. So this is not a standard defined procedure. This was kind of an implementation specific, but the standard also mentions that you can access these capabilities without even having security. So it's up to the operator to implement this. Some operators can actually implement after having security, some can do it before security. So I will show some results after this. So basically the relay is trying to modify these capabilities, and the phone, neither the phone nor the base station nor the core network can actually detect that this kind of modification actually happened. So what happens, the base station get the capabilities, it will send it to the network, like to the core network, and the core network actually saves these capabilities. How long, it depends on the configuration, but what we have seen is up to, until you restart your phone, it's saving at that core network, and then whenever the base station is actually asking for the capabilities, it would send back, because the base station needs these capabilities to do some optimization over the air. So once the capabilities are modified, for example, like what kind of modification we do, we change, the first thing we change is, like, we change the category. Like I said, higher processing device has higher category. Not exactly all the time, but there are devices like Cat 19 and Cat 20 which were recently defined by the standard. They are generally referred to IoT devices. So if you're taking the higher processing device like Samsung Galaxy S9 or something, it is actually a Cat 12 or Cat 16 device. So we are trying to replace the category. We are trying to put it to Cat 1. So Cat 1 is nothing but a device like which operates like an IoT device. So this category was defined for IoT. And then you're trying to remove the capabilities, for example, like the carrier aggregation or the MIMO, multi-input, multi-output systems. These are some of the new technologies which were used in 5G to actually boost speed. So you receive signals from multiple places, and then this actually helps boosting the speed in 4G. So we try to disable this. Then we remove frequency bands. Like if you are on LTE, you should support certain bands, at least 2. So you can have handovers and stuff like this. And then we have something called voice over LTE, which was specifically making voice calls or SIP-based voice calls on LTE, or else you have to go back to 2G or 3G and then do voice calling. So being a man-in-the-middle attacker, we try to remove all these capabilities and completely go undetected, because there was no integrity protection, so a modification cannot be detected. So this is a screenshot. I have the special phone which actually shows you the traces that are actually happening between. So this is from one operator. So what we see here is like the capability is actually being, the capabilities are requested before the security mode command, so which gives an attacker an advantage to actually modify them. So we try to test this on different networks, even though it doesn't really matter, like if you are having an elite SIM card, because sometimes like if you are having a very good SIM card or like elite connection, you get really good speed even if you are in a big fest or a big venue like this, because you are entitled to receive. So even having an elite SIM card doesn't give you more speed if your device doesn't support. So we tried some experiments with iPhone 8 and then also a Netgear router. Both are actually Qualcomm based. So this doesn't really apply to Qualcomm, but it applies to everybody. So it's a problem with the network operator. So it's not the problem with the baseband. So what we saw was like once the capabilities are modified, the speed was reduced from Normally it was supposed to receive 48 Mbps, but it actually receives like 2 Mbps. This was somewhere in midnight, but if you test in like normal high peak traffic time, I think you cannot even open Gmail or which it makes it difficult. Like it goes to kbps speed. So voice over LTE calls are denied. So whenever we make a voice call in this situation, the phone is kicking back to 2G because it doesn't support voice over LTE. Then handovers, like it's not being handed over to a 4G base station, but it's being handed over to a 2G base station because the phone doesn't support it doesn't support LTE bands. So these are like, this is something like you're killing the service and then you're actually downgrading the device. So to keep it simple, like you're actually connecting a high-end device like an IoT device. And then you are killing the speed and then you are downgrading it. So like I said, we tried on different networks, different countries and different continents. So 22 networks were actually requesting the capabilities before security, so which are actually affected. And then the main problem here was the persistence of the attack. Like, because the network is actually storing these capabilities, maybe 7 days, the kind of experiments we did. So 1 week, until unless like I restart my device, it's not going to regain the service back. Like I said, like the radio is a bottleneck for high-speed data services, so this applies for any kind of high-speed device. You could also test it with IoT devices, but anyways, like IoT devices are made for operating on low speeds, so it doesn't really affect them, or it doesn't really bother IoT devices. I think this is more targeted towards high-speed devices. So you might ask me like the question like, okay, why is the standard allowing you to actually send the capabilities before security? So there are reasons, for example, like to do optimization prior to security, like optimize the radio network so that the later data connection like goes smooth. This was, I think, one of the reasons we found in the standards. Yeah. So the third attack is something we are doing with the battery drain. So there are new devices in the market called narrowband IoT devices. These are, and they have a special feature, something called power saving mode. So basically the device, and these are the devices like you find in like smart metering or in applications where the device is sending just few bytes of data and then has nothing to do after that for maybe like 1 week or something. Also even smart grids. So basically the device enables this power saving mode with the help of the network, and then it sends some data and then goes off for some defined amount of time, maybe a week or something. So basically, being a man in the middle, what we are trying to do is like we are modifying the capabilities, since there is no, like I said, since the security is actually kicking after the exchange of capabilities. So we try to remove the power saving mode. So the problem here was like the phone is, okay, even though if the phone supports the power saving mode, it doesn't activate unless until the network is telling to do so. And the network doesn't activate the power saving mode unless until it knows that the device supports. So what happens here is like the base station, the relay or the man in the middle is trying to disable it. So network thinks that it doesn't support any power saving mode, so the device is actually on for the rest of the period. When it's on, what a modem is doing is like it's just trying to read neighbor cells, like do some measurements, always trying to scan for new base stations and then trying to camp on them. So this is kind of like wasting power actually, which is not really the main purpose of designing these type of devices, because they are destined to operate for 10 years on a single battery, or on a AAA size like 2 batteries. But what we saw in our experiments was like we are killing the battery lifetime by like 5 times, and then again the problem is with the persistence, like it doesn't go away if the attacker is gone, because the capabilities are actually stored at the network. So you have to manually restart the IoT device, like which is I can imagine like hard to do it. And then this drains the battery like very quickly, and the problem was like this was not able, this cannot be like detected either by the phone or the network. So this was the problem that was existing in the first release of narrowband IoT devices, like it was called release 13. Then release 14, there was a fix for that. So all these vulnerabilities, like we actually reported to GSMA and also the 3GPP SA3, which is doing the security part, and also all the affected vendors and even operators. And actually, I should thank GSMA. Like the process of reporting the vulnerability was very smooth, and then we could get the fix, I think, in 1 month. So there was also like a fix in the standard by the SA3. So now the network has to request the capabilities only after establishing a security. So this should be something done, updated, or by the operators too. But even though with this fix, still the fingerprinting attacks are possible on 5G. I think I just forgot to mention, because the narrowband IoT testbed we used was something, we don't have any like open source implementation of the narrowband IoT network. So we approached a vendor, like an operator, so we could borrow equipment and then do some man-in-the-middle attack with that. But LTE, like for 4G, like we have some kind of devices, like some kind of open source software, where we could actually do the attacks and see how it's working. So, like I said, the Nmap is still possible on 5G. There was some kind of discussion which started in 5G regarding fixing these capabilities, because being a passive attacker, you can actually listen to thousands of capabilities and just fingerprint like what device is this and everything. But I hope maybe in 1 year or something there should be a fix for this. But it's a basic problem. It's a fundamental problem which was there, and which might increase, because with 5G, like you have more applications coming in, and then you have more capabilities that are actually exactly defining what kind of device it is. So you don't have to do this much of fingerprinting if you're going in, for example, like take 2021, if you don't define this, then the fingerprinting becomes more easy, because the capabilities can really say, just by looking at that, you can really say what kind of device is this. So for fixes, like I said, I think the current versions of narrowband IoT don't really have the fix for this. The fix is like the device is sending the core network capabilities to the network, and the network would replay them back to the device after establishing the security. So that you can actually verify if the capabilities were actually modified in the beginning. So like a hash of them. So this is actually there in the standards now, but I haven't seen any vendor actually implementing them. So it's a release 14, so kind of quite new. So maybe next year or something we should see. And I'm not really aware of. I'm actually aware of some operators like which are actually out of those 22. I'm actually aware of some of them, but I don't really know who is the vendor or something, because I couldn't get enough information from the standards or the GSMA. Like it was kind of, it kept secret. Or so operators really have to implement. We are not really sure if it's an implementation problem or if it's a configuration problem. So both really have implications on this, and changing them, I think, would really solve the second and third attacks. Yeah, so that's it about the new attacks we found on 5G networks, and then let's see what comes in the future on 5G. Thank you.